Good afternoon, everybody. Welcome to this next session in the openBIM Awards 2024. We have two categories in this session. Those categories are professional research and student research. I'd like to get started straight away. We are going to hear from Mostostal Warszawa, and I would like to invite Piotr to the stage. Thank you. And David, yep, and colleagues, please.
Good evening, everyone. We are pleased to be among the finalists of the Building Smart International Awards competition. Today, we will present our outcomes that have been developed and tested in a real construction site environment. We will show you how next generation Internet of Things platform using openBIM and AI can improve health and safety on construction sites. My name is Piotr Dymarski, and together with my colleagues, Witold, Agata, and Dawid, we will provide you with more details about our projects. We represent a construction company called Mostostal, which undertakes all types of construction projects. Our motto is "We build the future," which we realize through the implementation of digital tools and execution of European research projects. Our company's fundamental values are innovation, safety, and teamwork. And all these values were taken into account in the projects we are discussing. To develop our solutions, we work for over 3 years together with experts in different fields. The entire project was coordinated by Universidad Polytechnica de Valencia, and our role was to prepare requirements from the end-user perspective, prepare IFC files, carry out the demonstration, test, and validate the technology. The construction sector is one of the most dangerous, the construction industry is one of the most dangerous sectors with very high numbers of serious and fatal accidents. Construction site is dynamically changing work environment. Additionally, due to a high numbers of frequently rotated workers, it's very difficult to supervise them. Our goal was to develop a tool for continuous monitoring of construction site safety, providing alerts about the potentially dangerous situation. We achieved that by connecting BIM models and information about the currently dangerous zones with Internet of Things platform and implementing AI. Before we cover our use cases in detail, let's move to our construction site in Warsaw. This contract had very extensive BIM requirements from the investor. We had to rely on Building Smart standards, which are foundation of our digital strategy. Thanks to use openBIM, it was possible to develop such ambitious and complex solutions for health and safety. We use IFC models for classification developed for this project, including, for example, hazard types. We use point clouds and 360 photos to create as-built documentation and models. To maintain the quality and accuracy of the model, we utilize communication in BCF format on a CDE platform. It's standard practice in our company that we implement on each construction project CDE platform for health and safety reporting. Based on the collected data, we display it in Power BI, and thanks of this, we can conduct analysis and draw new conclusions related to the health and safety. And now, here's Witold to tell you more about these activities and other use cases on this project.
Thank you. So I will continue by showcasing how we went above and beyond in creating our innovation. Our use cases are a direct response to hazardous situations present at construction sites. And of course, at the core of the Internet of Things is the hardware. We developed custom equipment that computed data from sensors at the construction site. We processed real-time images from a camera, for example. Additionally, we used ultra-wideband antennas for the localization of incidents. Here, the combination of physical measurements and coordinates read from the IFC model and tasks in a common data environment allowed us to have a localization system up and running. All workers were equipped with a location tag, as well as a smartwatch that served as an interface for worker-specific alerting. And for OSH manager, there was a dashboard created for a tablet where he received all the alerts. Of course, connectivity and software integration of these tools were established to then create one Internet of Things. And now moving to particular use cases. To assure workers' health and safety, we measured pulse of the workers in case of abnormalities. Both the worker and then OSH manager were alerted. Here, importantly, the alerts contained the location of incident as well as workers affected workers' data. We were also able to detect entry into modeled danger zones. The integration of IFC danger zones parameterized with type of danger as well as validity date allowed us to inform worker about the active dangers present at the construction site. Here, to furtherly streamline the process of modeling danger zones, we modeled them natively in IFC. This was important to keep the models up to date. We successfully used freeware here, exactly Blender BIM Bonsai, and then thanks to open-Ecole collaboration, an application was developed which allowed creation of zones on a tablet, also with direct integration to the Internet of Things. As an extension of the geofencing use case, we were able to check workers' permissions upon entry into a zone. Also, thanks to a camera capturing pictures at the construction site and a custom AI algorithm, we were also able to detect workers entering construction sites without a protective helmet. Here also an alert was issued. One of the challenges that we encountered was the algorithm having problems with differing between a bald head and a helmet, but we fortunately overcame that. Thanks to an accelerometer integrated in the location tag, we fed and trained an AI algorithm for fall detection. Both falls from height and falls from the same surface were detected. And here, crucially, both neural networks and knowledge graphs were used to provide a reliable algorithm. Then, as a further step in digitalization, we moved report creation to an augmented reality interface. This was, of course, conveniently integrated with the localization system and the IFC model. We also explored marking and evacuation route in an IFC model for the AR interface. So, in summary of the use cases, we tested and demonstrated our solutions in a relevant environment of a live construction site. We achieved high user technology acceptance, low latency, and low false positive rates. We successfully proved the concept of an IoT utilizing integration of an IFC model with for the real-time support of occupational health and safety. And by implementing open standards every step of the way, including openBIM, but also open standards for connectivity, for software creation. We assured high scalability. This means that this platform that we develop could be easily extended for any other use case. Now I'll give floor to Agata.
It is important to highlight the significance of using openBIM in the project and the role it played. The software ecosystem map has the openBIM component, openBIM model, IoT key component at its center. It is the heart of the entire system, and just like the heart is vital for an organism to function, this system could not operate without this component. The openBIM standards were applied across various areas of the project, including design and modeling, the use of CDE platform on the construction site, as well as mixed reality. Especially the use of BCF, bSDD, and IDS were triggers that powered the IFC model of the building, functioning like one of the heart chambers. In the model, we included elements typical for the construction site environment, focusing on hazard zones. Here, the bSDD service proved helpful. By creating our dictionary, we ensured that all model elements were correctly classified. Properties assigned to all hazard zones, crucial from the perspective of construction workers' health and safety, included, for example, hazard type, valid until, and risk rating. We used Akka bSDD editor to create our dictionary that we then uploaded to the bSDD service website. The publication of the bSDD allowed Mostostal Warszawa as the first organization from Poland to appear on the list of entities using the bSDD service. At the moment, we have 5 different building smart data dictionaries published. The information layer of the IFC model was then verified using IDS specifications. In the process of creating IDS, we directly referenced classes previously created in the bSDD. For example, we checked whether the hazard type has the correct value from the list of hazard types, and also if the hazard zone has its duration defined. Different IDS files were then uploaded into different software, BIM Vision Program, Solibri Office, and BIM Collab Zoom, providing us with verification reports. Heading towards the conclusion, we have transitioned from OSH reporting on paper into reporting it on CDE. And now we are developing AI-based real-time reporting with the use of augmented reality. None of this could have been achieved without the use of openBIM. That makes the solution open and accessible. But what is the significance of our project that makes it not only a research work, but also a research work with a very concrete, practical, and implementation dimension? This is what Dawid will introduce you to.
Thank you. So by placing openBIM standards at the center, we brought many benefits on project and company level, including developing bSDD and IDS for other projects also. At the educational and industry level, we contribute to the Building Smart Poland annual report and the Collier's report addressing digital sustainability challenges. Also, the project resulted in many interdisciplinary publications, bringing in meaningful academic results. And also, for many years, we are involved and focus on transferring practical knowledge to the students. We organize workshops where they can use our IFC models, and we like to teach them about openBIM standards used in practice. We presented achievements at the both national and international conferences. Also, we actively promote the use of openBIM standards in the Polish market, and we work together with software vendors to create and improve better software for all users.
Key openBIM outcomes cannot go hand in hand without addressing sustainability aspects. We align our solutions with 7 of them. In conclusion, our project supports both research and practical benefits. For example, open access to results, gender balance in research, and impact on high-quality education. Sustainable development in the context of the built environment is widely understood as recycling and reuse of building materials. Nevertheless, it must be highlighted that it is humans that sustainable goals are aimed at and for. Construction workers' safe and decent work on the construction site that the project contributes to are directly aimed at construction workers, that is, at humans, their health and their lives. Thank you very much for your attention.
Thank you. Next, I would like to invite Arghavan to the stage from the Eindhoven University of Technology. Yeah, no problem.
Hi everyone, just one question. Does this work? Okay, sorry. Hi everyone, my name is Arghavan from Eindhoven University of Technology.
And I'm Vitalij Tetervov from BIMbox.
We are proud to present to you our project Use, Reuse, but Do Not Abuse Resources, an openBIM approach to standardizing terminology, data, and processes for circular construction of information management and exchange, a project that received funding from 2 European projects. Why are we doing this? So what you see on the board is country overshoot day. I'm based in Netherlands, so I make that as an example. In Netherlands, on the 1st of April, all the resources of one Earth is already consumed if all the people on the planet live like we do in Netherlands. And that means that for the rest of the 9 months, we are borrowing resources from our future generation and our future, our own future. So by doing that, we are lowering the regenerative power of the planet Earth. And therefore, we need to be conscious about how we are consuming, and we are at a critical point in our history where we have to go toward resource-efficient approaches. On the top of that, built environment is responsible for more than 30% of the energy and carbon emission production, and that's because materials such as steel and concrete are notoriously energy and emission intensive. One solution to tackle both of those issues, resource efficiency and also energy and carbon efficiency, is to focus on reuse in line with the principles of circular construction or circular economy. And that's because every time that we reuse, we are basically skipping the first 3 life cycle stages of a material or a product, and that is extraction of raw resources and also manufacturing. However, if we want to reuse, we need to find the stuffs to be reused. And that's why we have a material bank. So material bank is a concept that on the physical side, we go and see if something is assessed by the material bank for its structural, environmental and chemical performance, so that it's safe to be reused for humans and everyone in the next project. So it connects 2 different projects together. But also on the digital side, we want to communicate this information to designers, practitioners, and contractors to be able to find these reusable items and use them in their projects. So we need visibility. This project actually started 6 years ago. So in 2018, BIM was still a little bit new. And we asked a futuristic question, how to connect the building information model to a material bank. And that was in 2018. We didn't really have an information model for this use case. We also didn't have a material bank. We just knew that in the future, designers are going to consult a material bank and find reusable elements from them to put them in their BIM model to see if it fit their design. on the top of everything that we had or not had. We didn't even know what information we should communicate in between these two platforms. So I started to look at different material banks in the industry and also in the academic literature, and I saw that the same siloed approach that was very prevalent in the energy domain is filtering into sustainability and circularity domain, because there are a lot of ad hoc one-off solutions that are not reproducible, they are not standardized, and they are not interoperable. Also, there were a lot of dependency on closed BIM approaches and also a lot of closed BIM software. So even if there were material banks, they were communicating information only with a certain software and the native data from that software. In case you have 3 different material banks in one city, then also those material banks were not communicating with each other. That's why we have openBIM. But even that time, the data structures were not supporting circular information or end of life cycle information. So the next step was to focus on how to define reusability. And there were a lot of confusion, it still is, about reusability. The first one is that sometimes when we say that something is reusable, we're actually talking about something that is in the current building stock. So we want to design with the existing ones. Sometimes we say something is reusable and we're actually referring to something that is built in 2024 to be reused in 2080. So there's a lot of human confusion about this term and how to untangle it. Then the next confusion was that there were a lot of good early research, but they were focused a little bit on short-termism and indexing things. If you're familiar with ESG, you know that we have to move toward more long-termism approaches. And for example, if you say that this chair is 76% reusable, you really don't understand which part of this chair is reusable and how to achieve that 76% reusability and not drop the percentage. So we wanted to have operational instruction for reusability and saying that back support is reusable if structural test results are okay. And the last step was, okay, how we want to make machine readable terminology out of this reusability definition. And at the time, reusability was defined as an intention to reuse. You cannot really model intention in IFC or ontology or any machine readable way. So it's too abstract, too unmeasurable, and also too subjective. And the idea was to look at information needs and requirements that we can objectify reusability so that it established a common language between us. And we started a 3-part methodology that was quite iterative. First one was academic literature review. It's a very comprehensive review, and we noticed that there are a lot of properties that are same for conventional materials and reusable elements and materials, but also new ones. Probably the novelty of our work is that we are relying on a lot of established industry standards, especially the upcoming ISO 59040, that is product circularity datasheet. If you're in the domain, you know that it's going to be published very soon. And it established a minimum standard for what information there needs to be there. The reliance on these standards was because we wanted to make sure that whatever we're proposing today is going to be usable for the next 10, 20 years. And the terminology is not only understood by us, but also by the future people. And in case there is a data obsolescence in the future, the terminology can be traced back and people in the future can understand what it is there. The next step was an interview with industry experts. The interviews were aligned with ISO 29481 because we wanted to produce some process maps and explain how these things are done in the practice. And it resulted in this taxonomy. So this taxonomy was first translated into a linked data ontology. You can see that this taxonomy is very well linked because the idea was to move away from binary dead ends that you say something is reusable, yes and no, and make sure that information has chain axioms. And you can also see that, for example, connection types, source type, and base codes are directly coming from PCDS. And also in the middle, you have circular potential that connects different things to each other and also to this extra information. In the next slide, I will explain a little bit more. But what I like to emphasize here is that this taxonomy is minimally structured for maximum impact. So you can use this for buildings, products, assemblies, sub-assemblies, and materials all at the same time. And also both for project information models and asset information models in line with ISO 19650. This is a small case study that we did to validate our project. It's a patented product design in University of Luxembourg. And you can see that with the, for example, circular potential for the whole product, we can describe it, but its remanufacturing potential meaning that it cannot be completely reused. Some parts need repair. On the product part, you can see that it's reusable, but it has a certification requirement because it's concrete. However, maybe the innovative part is that this bolt cannot be legally reused after it is used in one life cycle, even if it passes the structural test. And that's because because Eurocode doesn't allow pre-tension bolts to be reused for the second life cycle. And these are the kind of information that we really wanted to capture instead of saying something is 70% reusable. So this was our case study, and now I move it to Vitalij.
Thanks, Arghavan. We've met with Arghavan at a BIM event, online BIM event in Liverpool, and I saw her research, which was great. It had taxonomy, ontology, but it was probably a leap forward for the construction for it to be used on day one. So we had a brief conversation, which led to a 6-month ongoing collaboration, with the first outcome being a data dictionary, which is now published on bSDD, and actually was used by someone in the previous presentations, which is great. You know, it's objective, it's machine readable, it has data types, many things. But most importantly, it's one of the first data dictionaries that look at the end-of-life properties that can be used by the industry professionals. At the same time, we thought it's great having bSDD published, but we need the practical application. So we looked at the array of software applications just to prove that this concept could be implemented using today's software solutions. So we mimicked the project in Revit and enriched the data using the openAC plugin, and then exported the IFC, used the BIM validation services by BuildingSmart to check the syntax, etc., and pushed all the information in the Blender BIM to check for the results. In addition to that, prior to that, we also created an IDS where we used OSBIM platform, where we connected to bSDD to use the same definitions, etc. Now, all the discrepancies were communicated using BCF file format, using BIM plugin, BIM Collab plugin. Now, this is a video just showcasing what has actually been done. But while it rolls, I would like to pick on a couple of challenges that we came across. First was actually translating the link data into bSDD or into IFC kind of terminology. So for instance, if you think about a functional layer, which could be a facade, it can't be represented in IFC quite easily. You need to concentrate on the separate entities like walls, doors, windows, etc. So we had to IFCify it, if you like. We also came across some technical challenges. We can define, dynamic properties. We can describe materials in nth degree on bSDD, and we can apply properties to different entities. But it doesn't necessarily translate quite easily into BIM authoring software tools, at least not yet. So hopefully it will be sorted by software implementers in the next couple of weeks, maybe months, maybe years. We obviously used IDS. Everybody loves it. But most importantly here, we thought this is great, but we need an approach that is actually translatable to the rest of the industry. So Arghavan took a lot of her research and pushed it onto use case management platform, so the industry can actually implement these workflows.
Thank you. So yes, thanks to BuildingSmart Benelux, we provided an IDM and UCM. It supports 9 different processes sequentially, but also it supports both design for reuse and design for with reusables. Everything that I said at the beginning is now solved by this entry. You can see that there are different process maps and information requirement, and also it supports all the way from a waste audit to the construction team, to material bank, to assessment for reuse, remanufacturing, and also design for both contractors and designers. We like to conclude our presentation with some openBIM elements and benefit. As we suggested in the title, we wanted to make sure that terminology, data, and processes are standardized. We wanted to enhance semantic and technical interoperability and move away from the information silos. More importantly, we wanted to provide a robust and solid infrastructure for other projects, as you saw earlier, that use bSDD, so that they can advance in their own way and contribute to circularity and sustainability. The project is in line with the ISO BIM standards for BIM and also a level of information need. It states it provides a state-of-the-art terminology, and it's a scalable solution that can be later used, supports BIM-based material banks, digital diagnostic, and automated sustainability. Thank you.
Thank you very much. And so we will move on to our third presentation in the category. And I'd like to invite Jacopo to the stage, representing Polytechnic University of Milan.
Okay. Hi everyone, I'm Jacopo Cassandro from Politecnico di Milano. I'm glad to be here to present this project that we are developing in collaboration between two different universities, Politecnico di Milano, Università degli Studi di Padova, and one public administration, Lombardy region, that is also the founder for all this project. The title of this project is IFC Cost, Redefining Cost Efficiency and Transparency in the IC industry. Starting from a brief agenda of this presentation, we're starting from a brief overview about the introduction of this project and the definition of the problem statement and research aims, moving on the development of the cost domain, the new cost domain based on openBIM standard, and the new construction cost estimation processes based on this new cost domain. And later then with the validation system compliance checking that we will develop using this cost domain. And then at the end, the result and the conclusion of this project. As we know, nowadays, in the construction process, we have a lot of data that are interconnected to each other, and the cost estimation is one of the key data, one of the key tasks that we have in our project. We have into the 5D BIM model all the data that come from the 3D model, but also the data that come from other type of, such as the 4D management time schedule, but also related to the cost that in Italy are cataloged into a price list that is a catalog of all the cost items. The problem statement is that nowadays we have the cost estimation document that are completely detached from the BIM model. We have cost items that are described in natural language with only a code as a matching key that we can put into the 3D BIM model. And in the other hand, we have the model, the 3D model, the geometric model that are structured and based on a standardized structure. Also, we can also exchange this model through IFC in IFC format to exchange to all the stakeholders and also practitioners in our project. Nowadays, the only way that we have in our commercial 5D BIM tools is to link this code of our cost estimation in natural language into the geometrical model through an attribute and put different code into this BIM model. This causes a lot of problem because we are also a lot of manual tasks error-prone, and also time-consuming. As I just said, nowadays we have these attributes that contain a lot of code, and for a machine it's impossible to understand the data and also validate this data between two different domains. The aims of this research is to improve the accuracy and create a more structured and more granular cost architecture based on a standardized way, and also create a real relationship between these two domains. That we have the cost domain with a standardized structure and the geometric domain. The aim is to develop a digital platform that ensure the relationship between these two domains, but also ensure future validation, future compliance checking about the information related during the cost estimation processes, and obtain a new enriched BIM model with also the cost information, not only with the geometrical information. Moving on then to the cost domain. As we know nowadays, the description of our cost item are only in natural language. We can see that these information are not linear and are scattered. We have a lot of information related to the work, resource, activity, and technical specification in the same description. This is completely understandable by a machine, and it's very difficult to understand also for the users and the practitioner the real application of this cost item in the cost estimation. The first way is to standardize and try to standardize this data and structure this data in a new cost structure. We developed this new structure based on two different parts. The first part, that is the work, that is related to the physical entity and can be related to the 3D BIM model, but also the activity that can be related to the time, to the schedule. And also we can also validate not only our geometrical model, but also the schedule and time schedule. First of all, we define this new standardized cost structure domain based on several relationships, and in parallel, we try to translate this new standardized domain in IFC format. We can see that we have the IFC cost item entity that can be described all this data, and also can describe all this data through the relationship between different information. We can also relate and nest different cost item into the main cost item, and also relate this cost item to unitary task and unitary and a sample element. We can put all this information into a set of attributes for each of these information, and structure the cost item not only with a simple description, but with a more complex architecture. As we know, each cost item related to the construction work is based on a price analysis. With this new structure, and also with this new entity, present in the IFC standard, we can also structure this price analysis based on several cost items nested into the main, and also define a clear and transparent price analysis, understandable also by a machine. We can also structure not only the information related to our cost item, but also we can structure the cost value related to each of these cost items. We can start with the definition of the cost value of our elementary resources, material, labor, equipment, product, and so on, and then up to the definition of our final cost value related to the construction work, with the relation with other also cost values such as overheads, profits, and so on. The construction cost estimation process with this new standardized structure based on openBIM classes ensure also a real relationship between the object, geometrical object, and cost element, cost entity. We can also create new cost entity into the model and enrich our BIM model with the cost information. We have the cost value that can be inherited from the cost database, and also the physical quantity of our cost item useful for the definition of the cost estimation moderate from the physical quantity, original physical quantity of our element. Also, this new structure and this new relationship between the cost and element ensure also the possibility to group this cost item into a cost schedule that represent our cost estimation. We can also define not only a single cost estimation in static documents such as PDF or Excel, but also define a partial view of our cost estimation, such as the cost estimation for the laying of the rebar, forecasting concrete, and so on, and then group this cost schedule into a final cost schedule related to the entire IFC project. The last part is the validation system compliance checking. Is divided in two parts. A first validation using the IDS, information delivery specification, that can be done in the first part of our work before the construction and the definition of our cost estimation and the creation of this relation between cost item and object element. And we can check and validate the model that we received. And also we try to understand if the model can be used for a correct cost estimation. The second step of our validation and compliance checking is based on a new code developed by the research team and research group that can be also ensure the validation between the cost item and the geometrical element. This is completely different between the current validation system because we have only the possibility to validate the information into the same domain, such as clash detection. In this way, we have the possibility to validate the information between the cost domain and geometric domain. Moving on to the results, we can see that this new, more complex and standardized structure of the cost item can be validated using a commercial and IFC viewer. We can see that all the information can be stored into each of these entity, and also we have a more complex architecture, readable and understandable also by a machine. Here we can see all the connection of the IFC cost item based on the logic of price analysis. Each of these entity contain the cost value, the physical quantity, and also the relation with other entity. Here we can see an example of one of the case study that we developed related to the cost estimation process. We have not only a simple attribute with the code, but a real entity related to the geometrical element. This is a slab with 3 different cost items related to them. And each of these cost items can also relate to other elements, not only into one element. We can also group this cost item, as we saw before, to a partial view of our cost schedule and relate this partial view of our cost schedule to the entire cost schedule that can be related to the previous cost schedule, but also to other cost schedule and to the entire IFC project. In the end, we can see here an example of the information delivery specification, one of the IDS file document that we created. And this is readable also by machine, but also by the human. And we test it with our model that we receive. We can see that not all the requirements are satisfied, and the requirements such as the fire rating and status are not satisfied. And when we receive back the new geometrical model with the correct information, we can also create our relation between the data and also validate this new IFC model enriched with the cost between this code developed by the team. We have also the possibility to view the report of the accuracy of our cost estimation and also validate this relationship. In conclusion, as we know, IFC is considered nowadays as a snapshot at a point of time, as a static reference. And with this project, we want to ensure the possibility to consider the IFC not a merely snapshot, but also a digital environment that we can use to connect and relate all this information, such as the cost information, the technical specification, the geometrical information, and so on, to ensure a correct relations and also a dynamic environment for all these data in openBIM format. I would like to thank all the research team, Professor Alberto Pavan, Claudio Mirarchi, Professor Carlo Zanchetta, and also Regione Lombardia, that is the founder of this project. Thank you for your attention.
Thank you. If I could ask you to remain there, and if I could invite the other two finalists back to the stage. There's the two microphones up there, so please just pass them around as needed. And I'm going to hand over to Emma, who's got the first question.
So this is for the second presentation. So you talked a lot about properties within the presentation, but you also spoke about the object decomposition and you went down to the screws. So in the practical implementation, are you expecting the design team to be modeling down to screws, or is there another method of including those objects?
I would say it really depends on your circularity goals, because for circular economy, every little piece matters. And if you have maybe 10,000 screws in, I don't know, one building, then recycling them might make sense. It would be quite a task to be able to like really drill down the information and model them. But it's advised that you do that, especially if you, in the future, for example, use a GTIN or GSI standards, then you can easily understand like what exists in the model, and maybe it could be more automated in the future through the identifiers.
Okay, thank you.
Do we have a question from one of the others? Yep.
I have a question to the third presentation. What I got, that you're referring to a solid wall, and you're relating this to your cost elements. So what are you doing if you have a layered wall or a wall which is composite of different material?
Yeah, thank you for your question. Yeah, this is a project that we are developing with the public administration based on a new vision for the price list in Italy. For what the relation between the cost and related to exchange, and also, I don't know, for the material, we can also try to change the cost item and re-upload the IFC and change the type of our cost item, because we have a catalog with all type of cost item, and we can also change this item based on the material of our element, based on the dimension of our element, on what we want.
Thank you. And Josie?
Well, for the first ones, for the Assist-IoT on safety, first of all, congrats to all of you. Incredible presentations. You are doing not facilitating our job here, but thank you. And all of you address it, thematics that are such important and new, and you are making a leap on each one of these ways. For you from Poland, can you please tell us how can you improve from here on two ways? Firstly, how can this be adapted to others in the industry? And what are you thinking for going further on your research?
Okay, so first of all, I would like to mention that we are implementing health and safety solutions based on CDE on every our construction site. So our approach is to put the foundation, and then we can scale up and step by step going further. So we implemented CDE health and safety reporting at almost 60 construction sites, and we are looking for innovations like if you have one construction site, when we see we can improve, then we are trying to scale on this project and then use this on the other projects. So basically, in practical implementation, we will try to use this in our company to other construction sites, but it needs also to have a few more steps.
Yeah, and I can add that we continue our research because you could see that we have different use cases, and one of the most easiest implement use cases on the construction site was visual detection. And already we are in another projects with the Universidad de Erasmus and institutes from CERT, and we concentrate on to detect risky situation and wrong positions of the workers on construction sites, and it also will be continuous of the work related to the visual detection and AI.
I would just add one more thing. IoT is one integrated system, but as Piotr said, you can take one use case and try to implement part of it or the whole use case separately in different sites. But also just when it comes to the integration of an IFC as the center of an Internet of Things, we had a lot of perspective from software developers and telecommunication specialists who normally don't work with construction sector at all, not to say with BIM. And they had really an amazing insight to the world of BIM and many ideas on how to implement it in different ways as well. Yeah. Okay.
Thank you all. Given the time, we're going to need to wrap it up there, I'm afraid. I'm sure there were many more questions, but we don't have the time to accommodate them, I'm afraid. So thank you all, and we will move to the next category of student research. First up, I would like to invite Cloé to the stage. And Cloé is from the School of Technology, Supérieure in Montreal.
Good afternoon, everyone. I'm Cloé Arnould. I'm a master, I was until the end of August, a master student at ETS Montreal, and I work on a project of development and implementation of 3 openBIM standards, which are use case, IDS, and bSDD. So this project was led in partnership with CANAM and under the supervision of Eric Poirier, who is also the director of the GRID laboratory. So first of all, I will talk a little bit about our project context, then we will look at our openBIM workflow, then I will explain you our process of quality assurance and quality control, and I will finish by giving you some key outcomes. So what about our context project? This project was led at a steel manufacturer company, CANAM, who is employing 3,500 persons with operation throughout North America. So this company has implemented BIM since several years, and that led them to develop some interoperability issue. So to overcome those interoperability issue, we decided to implement new openBIM standards in addition to those they were already using. So we decided to work with use case management, information delivery specification, and the Building Smart Data Dictionary. So we first had a look on the use case. We asked ourselves, could the use cases help our collaborator to better understand BIM and to standardize our information? So we begin with the identification of 20 manufacturer use cases in order to create a manufacturer use cases database for a project. Then we develop and tested a use case identification workshop to involve our collaborators into the project. We then tested the workshop and made our collaborator identify 17 use cases specific to the company. We then validated those use cases by a survey and developed a use case template in order to document those use cases. And inside this use case template, we included an IDS section to link those two concepts, to give more meaning to the IDS standard for collaborators. So after that, we'll look at the IDS standard. And we ask also ourselves a second question: could IDS capabilities be augmented by the bSDD? So we first established a test plan composed of 3 steps. The first step was to develop simplified IDS, just in order to understand the concept and to be able to produce IDS that were actually working. The second step was the exploratory IDS development. Here, the main goal was to find as much as possible problems regarding the IDS development and to solve those problems. And finally, our last step was the focus IDS development. Here, we focus on the problems that we didn't succeed to solve in the previous phase. So for those 2 last steps, we'll look at 2 characteristics of IDS development. We'll look at the code and we'll look at the check capabilities of IDS. So for the code, we compare IDS that weren't developed with bSDD and 2 IDS that were developed with bSDD. And we did the same for the check capabilities comparison. In order to test our IDS, we use a model that have been modeling in Tekla and then exported in the IFC format. So, as I was explaining, for the code comparison, we compare IDS with bSDD to IDS without bSDD. And we also compare the code produced by 2 different software, Planoly and Has-Been IDS editor. We did the same for the check capabilities of IDS. Again, IDS with bSDD and IDS without bSDD. We compared the result of 2 different software, BIMWorks and Has-Been IDS. So here you can see some results of our IDS checks. You can see that we develop IDS for 3 different projects: BIM, Plate, and Bolt. Here you can see on the graph of the BIM that there is no missing information or invalid information. But if we look at the smallest project here, like Plate or Bolt, there is some red. So that means there is some missing information or invalid information. And that's why IDS is really useful, and that's how we convince Canon of it. Because it's impossible to check every bolt just clicking on each bolt one by one. And with IDS, we were able to find those problems in about, I don't know, maybe 20 seconds. And it was a very, very small model, as you were able to see. So imagine with a more huge model. So it's a very useful tool. What about our outcomes? So during the test phase, we developed 81 IDS. So we are talking about 3,747 rules that were tested with 3 different software. And as final outcomes, we developed an IDS catalog composed of 103 rules for BIM, Plate, and Bolt. And we also defined some recommendations about IDS development. So after that, we'll look at the use case standard and the IDS standard. We ask ourselves, could we use the bSDD in a more larger scale inside our project? So we'll look at the IFC enrichment part. So we enrich different IFC model using has-been bSDD. So during the test phase, it's 54 data that have been enriched in different models. And during and as final outcomes, we enrich 25 in one IFC model in order to test our final IDS catalog. So now you may be asking yourself, where all of this has led us to? That's an excellent question. So if you can remember, we first look to improve the user awareness. Then we made them identify some use cases. Based on those use cases, we define our information requirements. We then translate those information requirements into IDS, and we check our models with those IDS. And finally, we enrich our IFC models if it was necessary. And all of this was in order to check our information requirements using 3 different openBIM standards: use case, IDS, and bSDD. What about the real life? That's a good question too. So we imagine the client will define the use cases and the information requirement for the project. Then, based on that, the BIM manager will be able to select the appropriate use cases inside the use case catalog with already some indication for the development of IDS. Then the BIM manager will select the appropriate IDS inside the IDS catalog or develop some new IDS using, for example, those tools. Then, based on this IDS, the modeler will model the project and it will export it in IFC format to check it with IDS. Then he will ask his or herself, is the property, material, quantity, or attribute existing? And is the data being provided? If not, we can directly enrich our IFC model, for example, using has-been bSDD. If the property, for example, is existing, but the data has not been provided, we go back to the step of the native modeling to enrich the model. And if all the information has been provided, we can send the IFC model to the BIM manager that will recheck the model and ask his or herself the same question. Are all the requirements verified? If not, the modeler should do something. And if yes, we can send the IFC file to the client. So this proposed process was developed to be adapted to different company and to be improved. For example, we didn't mention the use of the BCF format, but it could be integrated. We can imagine some comment exchange between the BIM manager and the modeler. And that's why we choose the software, because they are all supporting the BCF format. Another thing, this process has been developed before the last update of the IDS standard and before the last updates of those software. So there may be some results that are not valid anymore. So what about my key outcomes? So this project succeeded to make a proof of concept of the applicability of use case, IDS, and bSDD for manufacturer. In a global way, we propose solutions that are working and immediately implementable. We also improve the current quality assurance and quality control processes by the use of automation rules. For the company, We improved the openBIM understanding of our collaborators, and we also made them believe into the openBIM usefulness. We propose an implementation, a process implementation that could be developed, and that made raise some new questions. And those questions were about the native enrichment part that we didn't look at during the project with the bSDD. So there will be more work in the future about that. And to conclude this project, this work has also been supported by the publication of my master thesis and a conference article. Thank you for your attention.
Thank you, Chloe. We will now go to the next presenter, Martina, who is joining us online and is from the Technical University of Denmark. Hi, Martina, are you there?
Yes. Hello, can you hear me?
We can hear you. So bear with just 1 second. Just if you could just advance one slide just so I can see that it works.
Yes.
Perfect. When you're ready, please go ahead.
All right. Thank you very much. My name is Martina, and I'd like to present my master thesis, which dealt with integrating lifecycle assessment data within the IFC schema using openBIM workflows. So the first challenge that I identified in the current LCA workflow was the siloed approach to information sharing across the different disciplines. So in the AEC industry, the different disciplines typically use different software, different formats and customs. And LCA as a concept deals with compiling these scattered informations a lot. And typically this responsibility of all of this communication lies on the LCA practitioner solely. So the lack of a unified information model makes this process much more difficult and time-consuming. Thirdly, still to this day, the most popular format for environmental product declarations is PDF. But even when these EPDs are somewhat digitized, they can't be easily integrated into the model. And this leads to a lot of manual data processing work for the LCA practitioner. This also creates a bottleneck in the iterative process, which is like the best way of creating LCAs. Lastly, there is a definite lack of detailed harmonized building LCA regulations at the EU level, which complicates the comparison of LCAs across different countries, and the lack of clear requirements for the documentation makes it so the long-term usability and storage of this data can be difficult. So generally, the concept of BIM and LCA integration has been a very popular one. There have been published many different projects on this topic. And here is from a very popular paper in this area, the 5 different primary connections of the way this can happen. And I identified that most of them rely either on self-made solution, that is some custom scripts or tools, or proprietary solutions, which often lack the transparency of the method. So common to all of these is a lack of standardization, a lack of long-term sustainability of this data, and a lack of connection to the underlying standards. So with my solution, I tried to focus on containing all of the data except the calculation itself inside the IFC model. And this was to create a single source of truth for LCA, and also use the IFC model as a long-term storage for the EPD data and the results. So the focus of the project was more on creating a systemic solution more than simply just a calculation tool. As mentioned, there has been a lot of research on the LCA-BIM connection, but much less on the LCA and IFC specifically. But here are the 5 primary sources that I used for my research. And the central dilemma in all of these was, should the environmental product declaration data be stored inside the EPD somehow, or just be referenced as external files, typically using a unique identifier, the UUID. I identified when we're talking about long-term storage, that is storing data for 20 or 30 or maybe even 50 years, this connection can be a bit fragile and problematic because there is not clear responsibility of what happens when the links get broken and who is hosting this data. At the same time, I realized that it would be unrealistic to ask people to manually input something, the EPDs, into IFC. So what was needed was a standardized and secure solution, which was also very easy for the end user. And my initial plan was to start this process by representing the full scope of the LCA as detailed information requirements, but that turned out to be a bit difficult because when I looked into these standards, they turned out to be very vague. Here you can see some snippets of the primary European standard on this area, and the Danish national standards were even more vague. So this wasn't something that was easily transferable to some properties, to the data types. So I started by compiling a big spreadsheet of the different sources, and I expanded my search to other sources such as other standards, guides, programs, and, for example, the EU framework levels, and many more sources that are not part of this of the final spreadsheet. And at this point, I also realized that there is, in the literature at least, a big difference between the building level information and the product level information or data. And on the product level, we have some better, more detailed sources, such as the ILCD plus EPD format. And on the building level, it was a bit more vague and difficult to find something. So while I was compiling this information, a clearer picture began to form of these connections between the core standards, but I still had two main issues. One was the information requirements on the building level, as mentioned, and I was addressing this with my big spreadsheet and trying to create consensus among the existing sources. And the other one was how to store the EPDs, even if they are in a digitized form. What should the connection be between them and IFC? And here I did analyze, as mentioned, the different solutions that others had gone through. For example, implementing them directly as property sets, using APIs or UIDs as external connections, or linking to other formats as XML or JSON. But it wasn't really a native IFC nice solution. So I tried to expand my search once again, because I thought the issue of having reusable products in IFC must be a more universal problem. And I did find the whole area of IFC for products, which, as far as I can tell, the projects go at least 12 years back. And it seems like they all culminated with this construction object data view project, which was started in 2017 by the CEN 442 BIM committee. And so in the original proposal, they identified the issue that right now, if a manufacturer wants to provide a product in the IFC format, they typically create an empty room in a random location, often Boston, and they place the product in the middle of that room, which isn't ideal. So they proposed in the first version of this project an MVD, which would include a header, IFC project library with the product data template, and an IFC project with the product data itself. And the technical documentation for this was published on bSDD's GitHub page for a long time. It isn't any longer, because this first version was withdrawn as a standard 2 years back. But there came a new version of this standard, which focused more on the configurable construction objects and had a very strong connection with data dictionaries and utilized some complex IFC concepts such as complex properties, declarative expressions, equations, and so on. And they also provided an example of a library object in the IFC format, which I also used. So at this point, while I was exploring these different solutions, I tried also to analyze how they would form a part of a larger workflow and context, such so the IFC model is not the only part, but also the requirement definitions and validation with IDS, and the different structures that the data dictionary look like. So I, for example, split up the information into national data dictionaries, European and global ones, and how they all could form a part of this workflow. And also this diagram shows different format possibilities, but as a core defines the layers of a manufacturer product catalog and a local IFC project library. So in the final solution, I did end up utilizing POD as a reusable IFC project library product, which could be shared by the manufacturers. And on the other hand, the EN 22057 standard, which defines how EPDs can be described as product data templates and be utilized in BIM. And this standard is format agnostic, so it only defines the property and data types. But for example, EPD Norway, they made a pilot project publishing some EPDs using this standard in the JSON format. And my solution was to take those EPDs in the JSON format and try to implement it all in IFC. And here is part of the implementation in IFC. I had a strong focus on finding good, efficient IFC mechanisms to try to represent this information, so to limit the duplication as much as possible. So to this, I use IFC tables, reusable columns, complex properties, IFC references, and so on. And also there was an in-depth analysis of how different scenarios, such as different future energy sources, which are it can be part of EPDs, also can be represented with this. Here is an example of defining an EPD at the material level. So an EPD doesn't have to be redefined for each element, but can be reused as a material, and it's only the amounts that change on the type or element level. And here's an example of this implementation in the IFC step format. As you can see, there are document references. There are the references to bSDD. There are the LCA phases are implemented as reusable IFC columns, and other information is implemented as property sets. The values, for example, were implemented as values in the IFC table rows. And that was my presentation. Thank you very much. I am starting a PhD in a bit of a different area, but I can still be contacted on this if applicable. Thank you.
Thank you very much, Martina. That brings us to the third and final presentation in this category. Making their way to the stage now, representing the Hong Kong University of Science and Technology, is Yuking Zhu and Xingbo. Please bear with us just 1 minute while we get your slides, and I'll let you know when you're ready.
Okay, it's ready.
Not just yet. Okay, should be ready now, yeah.
Okay, thank you. And good afternoon, everyone. Thank you for the opportunity. We are research team from HKUST, and I'm Terence, she's Rainy. we are both PhD students. So we want to use the openBIM format for the carbon assessment and tracking. So because we find out that the interoperability is very important in the carbon management, and the many people and the software are involved in this kind of process, and the openBIM can help us to link them all. So why we are interested to, sorry, the background didn't move. So, okay. So why we are interested in this project? Because we all know that the construction industry contributes 34% of the energy usage, and also contributed 37% of the carbon emissions in 2022. And we also know that the carbon neutrality targets is all over the world, like the World GBC or even HKGBC. They all set some target for the carbon emissions, like the embodied carbon and operational carbons for the construction industry. And then we want to know that what is the embodied carbon and the operational carbon. So we take a look at the LCAs. In the LCA's A stage is the embodied carbon, which was focused on the product and the construction. And for the use of the building project, it will be the B stage from the B1 to B7, and the C stage is the end of life. So in this project, the A and B stage of the carbon emissions is mainly discussed. And also we find out that the openBIM can help a lot in these two different stages of the carbon management. And also we want to know how to manage the life cycle carbon efficiently across the different stages and the multiple stakeholders. So, but it still have some challenges now. Like for the first challenges, it's the calculation of the embodied carbon is not clear for now. And we want to, the current calculations is referred to local database. And also we need to know what is the material quantity and even is the BIM model's accuracy or not. That's related to this part. And also because the embodied carbon linked to the multiple stakeholders like the suppliers or the contractors, the designers. So we need to make sure the data exchange is fluency and the data is correct. So the corroboration part is also need to be discussed. And then it's about operational carbon part, which is for the LCA-B stage. So in this part, we need to use a lot of the energy modeling engines or simulation engines. So for that, the openBIM, the format of the different kind of the BIM models or different source data need to be integrated into one format or in one platform. And for the last part, we also need to be discussed about the supply chain, because the carbon footprint need to be tracked during this process. And also in the commercial world, the data security is very important when we talk about the supply chain. So we use the blockchain for that. So overall, our problem statement that we find out the blockchain helps a lot during this process because it have the property of the interoperation and open, reliable, which can help a lot. So we developed our own workflows. So let me briefly introduce about that part. So for the first part, any kind of the BIM models, even from the Revit, from the Bentley, we can convert it to the IFC files. And based on the IFC files and the developed MBD, we can get the information which is embodied carbon required date. And based on that, we can quantify the embodied carbon. And then we also do some collaborative model enrichment and automated checking, which based on the IDS and the US BIM or something else. And then for the operational carbon part, we developed something which would work for the energy and carbon simulations, which for the operational carbon in the stage B. And last, we also focused on the supply chain. So then I will talk about the first part, automatic embodied carbon quantification first. And in this part, we firstly developed ontology, which is work for the embodied carbon. And then we convert this part to MVD, which can standardize the information requirements for the IFC scheme using MVD. and we can get all the information we want for the embodied carbon in this part. And then the data collector of the embodied carbons is using Dynamo or any other programming language for BIM. It also works. So by this way, we can get the embodied carbon results. And we can see the family types we get in this work, in this part. And then it's about the collaboration part. For the collaboration part, we firstly do the BIM exchange process using the IDM. And then we use the enriched IFC files or any carbon-related information put into the IFC files and get the final can be used data exchange format in the IFC in the openBIM file. And then the operational part is something similar to the embodied carbon things. We firstly developed on knowledge graph, and for the operational carbon, it shows here, which have 4 different types: the HVAC, the heat, or the building itself, and also the weather. So this different kind of data, we transfer them according to the bSDD, the Building Smart Data Dictionary, to make sure it can be fit for the IFC format and the other open standards. And then we use this different knowledge graph. We use this knowledge graph to get the different information source and stimulate the engine to get the operational carbon and support the dynamic data conservation for the automatic BEM and the operational carbon simulations. And we using the Energy Plus and even the Equest. And then for the last part, it's about the supply chain part. It have 4 different functions. The first one, we use the openGIS for the A4 stages because the transportations of the supply chains, it need to be counted as an embodied carbon. And also the design and actual carbon comparison and the visualizations also can be relied based on the openBIM and openGIS integrated platform. And then the operational carbon simulation is also be done in this step. For the last part is the blockchain-based construction carbon footprint tracking, which we want to make the carbon data can be tracked to the source and makes the result more accuracy. So overall, our methodologies is genetic method for all the buildings, and it have different steps to get the life cycle carbon emissions in constructions. And then we also have some illustration examples. So let me invite Rennie to do that.
Yeah, thanks, Terence. And next, I will briefly illustrate a case study of OPAC2 project in Hong Kong. This project is a special project since it is the first and the demonstration project in China to achieve zero carbon during the construction project. And this project has been completed. During the process, first, we developed the NVD, as we mentioned in the methodology, to extract all necessary information required for design embodied carbon quantification. And this slide shows a specified model view and the standardized IFC schema based on the NVD we developed for OPAC2 project. And then, based on under the model view defined by the NVD, then we develop a Dynamo plugin to automatically quantify the design embodied carbon results. And in this part, there should be a video. And in this part, this results of design embodied carbon will be generated automatically in the Excel format, which will be further imported to our developer platform, CarbonSmart, for assessment and blockchain-based tracking. And in the next part, here we use the IFC which is generated from the NVD-based extraction to link with model enrichment algorithms to realize IFC extension. And here we can see this is an example about how an original IFC file be extended based on our developed IFC extension algorithm. And from this example, we can see that finally, the actual use of construction material information, including actual material type, emission factor,
data and origins have been successfully added to the IFC file. And after enrichment, we use the IDS to better specify the data information exchange requirements, especially to ensure that IFC files have fully contained material information required for actual embodied carbon quantification. And in our example, we want to make sure all structure elements have material properties. So we developed machine interpretable IDS file and imported this IDS file together with enriched IFC in Blender to realize automatic checking. And then we can get the automatic checking results from the Blender interface and also a HTML report generated by Blender. According to these checking results, we added the missing information to improve the accuracy of carbon quantification results. And then for operational carbon, here based on the integrated KG and the automated BEM method developed in our research, here we used the openBIM to link IFC information to the energy simulation engines eQuest and Energy Plus. And finally, we can get the results of the energy simulation as well as the operational carbon estimation results. And in this part, we also try to evaluate the efficiency of our proposed method about the KG-based automated BEM method. And here we can see that by comparing with the manual building energy modeling process, our method can keep the consistency with manual modeling results. At the same time, our method can reduce the BEM model development time by 99%. And finally, for the supply chain results visualization, and here first in our developed platform CarbonSmart, we first can get the openGIS-based A4 embodied carbon quantification results. By using the GeoJSON format based on the OGC encoding standard, we encode the location data from the extracted from the enriched IFC. And then by using the Open Route Service API, we can directly get the transportation distance and also the transportation emission results in this stage so that we can improve the green procurement practices. And this is the 4 calculation results in our CarbonSmart visualization, including the embodied carbon results and also the operational carbon estimation results. And as I mentioned before, during the process about the carbon management along the whole construction life cycle, actually it involves a lot of data transferring during this process. So we also use the blockchain to secure and track carbon footprints in our platform. And in fact, OPAC2 project is only one illustration, and our method also be illustrated and implemented in other projects, including civil engineering projects such as the MTR project in Hong Kong. Finally, as a summary, I want to summarize the benefits of in our research using openBIM and openGIS. By using openGIS and openBIM tools, it helps us to improve the carbon management practices along the construction life cycle, especially the use of IDM, ERM, and NVD help us to enable better carbon data management in BIM models. And by using IFC IDS, it helps us to extend the depth of BIM and also enhance the high quality collaboration among different stakeholders. And by using IFC, NVD, and bSDD tools, it helps us to enable accessible digital twin to simulate operational carbon. And finally, openBIM tools also help us to facilitate a common data environment for carbon management software development. And this slide shows the key outcomes of our research. And finally, we help to improve the carbon management process more standardized, accurate, and automated so that we can contribute to sustainability and carbon reduction. And in the future, we hope to extend our work to the MEP systems and also to extend our work to the more scope of the LCA lifecycle stages, including the beyond upfront embodied carbon and the end-of-life stages. And this is publications related to our work. And finally, we are also very lucky to get some honors and awards from this work. This is team members from HKUST. And last, thanks for your attention.
Thank you. Thank you for wrapping up quickly at the end there. So I would like to invite Chloe back to the stage, and if we could please get Martina up on the screen, who was online. There we go. Just checking we can still hear you, Martina.
Hello?
Yep, that's great. Okay, so we'll do a question each, as we've done in the other categories. Question to each project. Whoever would like to go first from the jury. Yep, Rasso.
I have a question to the second presentation. Living in Denmark, you said it's not always easy to find the life cycle data, but you obviously found the ÖkoBauDAT from Germany. So how do you then work with this German ÖkoBauDAT in Denmark?
My project didn't focus on this source of EPD data. So ÖkoBauDAT is a great source of generic data, but EPDs can both come from specific product manufacturers for specific, as they are called, specific data, or generic data. And the question is how both of them can be combined and stored in the IFC, for example. So the architect or the LCA practitioner doesn't need to do any additional data processing of it. ÖkoBauDAT has done some projects with ILCD plus EPD, for example, and there is a detailed discussion of that usage of that format and the challenges with it in my project. It was a bit too much to go into in this short presentation.
Okay, thank you.
Hi, congrats to all for reaching this phase. I will ask for the last one. Congrats for your work. At a certain point, you explained that you needed to extend it and enhance, let's say, IFC in order to fit in the rest of the workflow. And how come that that way of working would be others could take advantage of it, but it could be something on demand by you and not, let's say, that others can take profit of. Can you elaborate a little bit about it?
Okay, so I think thanks for your question. So I think maybe also notice that our carbon quantifications follows the different stages from the design stages to the actual construction stage. And actually why we design these, that's because we want to, in the real practices in construction projects, they are asked for carbon reductions. Yeah, in that case, so we want to first identify the design stages, the carbon emissions, and then for the real actual construction practices, we want to record and also so that we want to quantify the real construction emissions, yeah, so that for comparison, we can get the carbon reductions and also maybe can review that some carbon reduction strategies have been taken by the stakeholders. Yeah, thank you.
Thank you. And anyone have a question for Chloe? Yep.
Thank you, everyone. Great presentations. Yeah, so for the first presentation, you're focusing on manufacturers, which is great to see. Did you look into the work around things like product data templates and ISO 23387 before making your decision to go down the sort of more openBIM path?
Thank you for the question, because it was actually the initial project to work on that subject. And you know, I think I had a lot of chance with this project, because my supervisor and CANAM let me do whatever I wanted to do. And the first thing that I really wanted to do was to listen to our collaborators. So I did many interviews to understand what was the real needs behind the project, because some director in CANAM asking for that, the template data, and they were like, okay, we need to create our data, I don't remember the word in English, library, sorry, our data project library to allow our client to have our information, etc., etc. And when I talk with our collaborators, I had the conclusion that they weren't able to understand why we needed this information, this data, project data information, what they were doing model, using BIM, what was BIM, everything was so confused for them. So we decided to begin with use case, and after that, we decided to give more meaning about this data project, not using template data product, but with something more logical for them. And it's like step by step with the different way that we took, that we arrive with openBIM standard. But at the beginning, that was what we were supposed to do. And we arrived at a point that we didn't look at that, because we listened to our collaborators first.
Okay, thank you.
Thank you.
All right, thank you to the jury here for the questions. Thank you to all of the presenters. That brings us to the conclusion of the research categories. Thanks for joining us online, Martina. We will bring this session to a close, and very shortly we will begin the final session with the design for buildings and design for infrastructure finalists. Thank you very much.